Now we are starting circuits, chapter 27, and first we will talk about single loop circuits. And here we will identify the action of an EMF source, electromotive force source, in terms of the work it does. And we will apply the loop rule to write a loop equation that relates the potential differences of the circuit elements around the loop. And we will apply the resistance rule in crossing through a resistor, and we will apply the EMF rule in crossing through an EMF. And we will calculate the equivalent resistance of resistors in series, and we will calculate the potential difference between any 2 points in a circuit. And we will distinguish a real battery from ideal battery, and we will identify that grounding a circuit does not affect the current in a circuit. And we will discuss all these items. And first, let's look at the battery. A battery does work on a charge in a circuit, right? It's like the charge pump. How much work per charge does it do? And this is called electromotive force. EMF comes from this, but it is not a force. Okay, so it's kind of a deceiving word. It's really a kind of a voltage. But we are going to be calling it EMF, and it is curly E. It's not really epsilon. I usually say epsilon, but it's a little curlier than what we've been using for the epsilon, so it's a little different symbol. So what is the definition? Since it's related to how much work per charge it does. So we have EMF, the work over charge. Okay. And if you recall this from chapter 24, this is really the definition of potential difference. Okay, and so here we talk about EMF, and we will show that it is really the voltage. Okay, and so some examples are batteries, generators, solar cells, fuel cells, human nervous system is even an electromotive force or EMF. And if it is ideal, it means that it has no internal resistance. And the real EMF has internal resistance. To the internal movement of charge. So basically, we see it from the previous chapter that when there's resistance, it's going to eat up some of the energy, right? And it's going to warm up, and there will be thermal energy released or heat released. And so ideal EMF doesn't have that internal resistance. That means it doesn't really heat up, and the system's energy is not gonna change because it won't warm up, or there's no electrical energy is not converted to thermal energy in that case if there's no internal resistance. But in real cases, and we will see those in the labs, we will have real EMF, real batteries, for example, and they will warm up because they have internal resistance, and we'll even do some calculations on them during the lab periods. So if you look at the energy in the circuit, first of all, the battery does work, as we mentioned. So rearranging that EMF definition, the work is EMF times dQ, right? And the resistor dissipate the energy. So you can see the load resistor here. And that is power times time is the energy, right? And since the power was rate of energy, if you want to write energy in terms of power, then you need to multiply by time. And remember, the power for a resistive device can be written in terms of I square R. And we also have dt here. Try to put these together, I square R dt. And if you recall the definition of the current, and write it for charge dq is equal to I times dt. Right, so we're just writing a bunch of things. We're going to put them together, as you probably guessed. So if you put these together, we know that the energy is power times time, right? So we are really putting the first two together. That gives us, so this comes from the energy conservation. The energy released by the battery is used by the resistor, right? So the battery pumps up the charge, that's the energy it has, and the resistor will dissipate that energy, and this is the energy that we found in the second line. So these two should be equal to each other because energy is conserved. So what we say then, for dW, we have E, which is EMF, times dQ from the first equation. And on the other side, we have I square R dt, right? So what we're going to do, we are going to get rid of dt. So we are dividing both sides by dt. So these two will go away. Okay. And we know that dq over dt is the definition of the current, right? This is 2, by the way. And so we have another current here. Let's just write that. This is the EMF times the current then. And we have I square R on the other side. So from this we get EMF being equal to IR. Okay. And that's the definition. So the EMF of the device of an, or the E of an EMF device. Again, it could be a battery or a generator EMF device, is the potential V that it produces. So that's what the EMF. How do we know that? Look at this equation. We know Ohm's law, right? V is equal to IR, and dimension-wise and the equation-wise, everything matches. So V should be like, EMF should be like V, so that means it's like a potential. Okay, it's not really a force, so keep that in mind. And after this, we will talk about the practice question and we will discuss some rules next.